next speaker is Soorya, who will we'll figure out what he's talking about very soon.
I always like to start with a black slide and fade into the first slide. It looks fancy. So, does it work? Oh, okay, that's fine. So, we'll be talking about estimating distinguishability measures on a quantum computer. This was a work done by Dr. Saab, me, Kunal, and Professor Willie. This happened over the summer and it's kind of bled into the semester, so we're kind of continuing to work on it. The idea was that, I mean, all of us here should probably know, but I'm just going to go over it, that fidelity, trace distance are distinguishability measures for states, and they're pretty important. We always want to know whether a state can pass the test of being another state, and how a protocol would vary, and the performance of a protocol would depend on these measures. And so, like I said, commonly used distinguishable measures are trace distance and fidelity for states, and then of course you can graduate them to distinguishability measures for channels like time distance and channel fidelity. And so what we show in this work is that these can be cast in the form of an interactive proof. I'll show you what a quantum interactive proof is. And like I said, you can generalize them to channels and strategies. One thing to note is that these distinguishability measures are efficiently computable by semi-definite programming. But there's a small caveat here. When I say efficiently computable by semi-definite programming, it's efficient in the size of the matrix. It's not efficient in the number of qubits, which is why we would want to calculate these measures on a quantum computer, which would be efficient in the number of qubits as compared to the size of the matrix would be exponential. So I'm going to give you a brief overview. First, we'll talk about quantum interactive proofs, and it kind of is been in the news now because of the latest result. MIT star Zari will talk about quantum interactive proofs. The definition, the fidelity and trace distance, which should be common knowledge, but I'll just go through them quickly. These algorithms, I'm going to show you some circuit diagrams of what we actually do and how they are, and some roadblocks we've kind of gotten into while implementing them. The results that we've gotten so far, and what we're going to be working on, and finally some open questions. So that's the brief overview of what I'm going to be going over. So the first thing we want to talk about is interactive proofs. So in an interactive proof model, there's always two parties, a verifier and a prover. And you should think of a prover as an all-powerful wizard who has unbounded computational power. The way to think about models like these are, supposing your verifier can't solve a problem efficiently, but can verify if a problem solution is correct. So a simple example could be, is this number prime? It's hard to find prime factors of a particular number, but if someone gives you the prime factors, you can check it. You can multiply the two and check if the number is the same number efficiently. So there are a class of problems that can be verified efficiently but can't be solved. Those come under NP in the classical case, and then you can expand the power of the verifier by allowing a prover who's all powerful. There's one expansion. Another expansion could be multiple provers, and that's how you get MIT star, and stuff like that. The idea is that the prover always wants the verifier to pass the test. So even if the input problem is not solvable, the prover will give a fake proof, and the verifier will verify that the proof is correct or not, and then go ahead. So the prover says you shall always pass. That's the idea. And the prover and verifier exchange messages. Usually it's one message, but you can increase the number of messages to increase the proving power, the verifying power of the verifier. So in a quantum, this is just interactive proofs in general. You can have a classical prover who's extremely powerful. In a quantum interactive proof, we just graduate all of them to quantum states and channels and give them qubit messages across. Sorry. So this is a diagram which I got from Watrous' paper on quantum interactive proofs. The idea is that you should think about it as verifier and the prover, and there are verifiers private qubits, uses for it, he or she uses for their own computation, and message qubit that they pass over, which is from the messages that they send. So that was interactive proofs. Now we're going to show about I'm going to show how fidelity of states and trace distance can be cast as interactive proof problems. The fidelity of states essentially expresses the probability of one being able to pass a test for another. And so for a pure state, it's essentially the overlap. It's just mod square of the overlap. But for two mixed states, it's this is a well-known form of the fidelity of two mixed states. It can also be written as a maximization over the something that looks like the overlap of the purification of the state. A mixed state can be purified in the sense that if rho S0 is a mixed state, it can be purified to psi rho. When you trace out the reference system, you get back your real state. That's called a purification. So the fidelity of these two can be written as a maximization over all possible purifications and the overlap of maximization of the overlap. So in the work, we show that the fidelity of two general mixed states can be written as a interactive proof. It looks like this. It looks very simple, but there's an underlying assumption that you have a description of a unitary that prepares the purification of the state. Essentially, ui acting on 0 and 0 creates psi I, psi 1, for example, from here, the first purification. U0 and U1 during the controlled manner. So the way to think about it is you should draw a line right through, and this whole lower half is a verifier, and the above half is a prover. So you do some local computation, essentially create a Bell state, do this in a superposition, you create both states, and you send one of them, and the prover does something which we don't know, but the prover always wants to maximize the acceptance probability, and it sends back one qubit, and then you do a Bell measurement essentially. So the verifier accepts if the verifier measures the state and gets a 0, 0. The probability of acceptance of this entire setup can be shown to be related to the fidelity of the states. So what we do in practice is run this whole thing on a computer and measure the probability of acceptance. And once you can calculate that, you can do some simple algebra and find out the fidelity of the states. So this is one of the algorithms given in the paper. I'm not going to go over the other algorithms because I want to talk about channel fidelity and trace distance and other interesting things. But there are about 3 or 4 more algorithms cast in the form of interactive proofs in the paper. So when you graduate this fidelity model to channels, we know that fidelity of 2 channels is just written as the fidelity of the state. Once you act the channel on an input state, you do a minimization over all possible inputs. This is essentially the same thing, right? So fidelity of 2 states. All we need is to do this minimization over it. And since we kind of have access to all powerful provers, what we do is we add another prover in the beginning who minimizes the input state. You just need to add one more prover to minimize the fidelity. So if you go back and look at the fidelity of states, the circuit diagram, all we do is add another prover here for the input state. This is another. So this is technically a prover that creates state psi. And sends it in, you do the exact same thing, and you can show that you do. If you remove this, this is essentially the exact same expression as before, the fidelity of states, and then you do a minimization over psi RA. And if you expand it out, you can show that it gives you essentially the same thing, the fidelity of the 2 channels. Again, there is an assumption that here you have a description that can create an isometric extension of the channel UI for that. So the 2 channels, N0 and N1. So that was fidelity, let's talk about trace distance. Again, it has an operational meaning in terms of hypothesis testing as a bias away from random guessing for two states. So this is how you just the one norm of the difference of the two density matrices. And this is a circuit diagram. The difference in the diagrams is that here we have kind of a cut in the middle, and these two are kind of independent of each other, so you can do it independently of each other. And that's how we kind of phrase the algorithm in the paper, where you flip a classical bit with 0 or 1. With 0, you create row 0. With 1, you create row 1. Do the entire procedure and measure, and you get I or j. And if I equal to j, you accept. That's essentially the same thing as running two of them and calculate the probability. So here P is the all-powerful prover again, who wants to maximize the probability of acceptance, and you have the two elements. But you can show that in this case, the acceptance probability is just again bias away from random guessing. Again, when you generalize this to the diamond distance of channels, you know that diamond distance of channels is just maximization of the inputs of the trace distance of the channel acting on that state. So we do the exact same thing. We add a prover to do the maximization, and you can show that the acceptance probability is the exact same form, diamond distance. So this was all the theory part of the paper and the circuit diagrams, but essentially, when you are putting this, when you want to calculate something on a quantum computer or on a simulator, we don't have all powerful results, right? We don't have access to them. So how do we go about doing this? So we replace all the all powerful wizards, the provers, with parameterized quantum circuits, and we optimize them. So this is an example of one of the ansatz that we use. For example, in the fidelity of channels, this is the ansatz that we use. We do random Y rotations, Z rotations, and then entangling gates, and then just repeat that multiple times. The assumption, which is kind of a hard thing to show, is that for choices of these parameters, these rotational parameters, every point in the Hilbert space can be reached. It's not proven yet, but most of the time it works out for a large number of parameters and larger number of repetitions.
But isn't the idea to have fewer parameters so there's less space to optimize over?
Yes, but
I guess there's a trade-off.
There's a trade-off. So if you have fewer parameters, for example, you can have one parameter and that would just be a rotation of one particular. If you think about a qubit, if you have one parameter, you would just rotate on one great circle of the clock scale. So you won't reach the whole space, but it would be more efficient to compute. But the idea is that we would rather have slightly less efficient, but cover the entire space. So I'll talk about the actual optimization. So usually when you do optimizations, you do gradient descent and just find the gradient with respect to all the parameters, and you take the parameter shift rule, and then you can do step sizes. Problem is that when you looked at problems like this, and this was just one of the provers, and fidelity of channel, you would have another prover with another 40 parameters. So if you have an 80 parameter space, gradient descent is just really slow, and then we were running into problems trying to get it to converge, and just really slow. So what we have come to realize is that we should either use a semi-gradient based approach or a non-gradient based approach. So the model we kind of ended up using was called SPSA, and in the interest of time, I've put it at the end of the after the conclusion, the definition of how SPSA works. If we can get to that, that'll be great. But the idea is that instead of doing every when you're calculating the partial derivative function, you do it with respect to every single variable. In the SPSA method, you do shift respect to all the parameters at the same time, simultaneously, and you can calculate a way to take a step towards the optimal point. Again, all the optimizers are from the Qiskit package. So I'll show you some results. So for the fidelity, this is the results that we got. in about 300 iterations, it converges to an absolute error of 10 to the minus 5. Similar for the trace distance. Okay. Oh, yeah. So Qiskit is a package from IBM. It's a Python package from IBM that has a lot of inbuilt functionality for creating states, quantum circuits, operators, unitaries. Basically, what we use for all types of simulations. And freely available? Freely available, yes.
And you can run it on the quantum. You can
execute
a circuit on a quantum computer.
So you can either run the simulation on your own machine, or you can submit a job, it will run it on a quantum computer and give back. Again, it's really small size quantum computers that you have access to, but still you can actually run it on a quantum computer, which is exciting. Yeah, so these are results. So let's just go over the. So we show how to cast the problem of finding fidelity and trace distance in terms of a quantum interactive proof. So we can use the results of the quantum interactive proof model. We also showed that extensions to channels like time, distance, and fidelity of channels. We showed how these algorithms run in practice, and we showed some simulations on this. All the simulations so far were on our computer, not on the quantum computer. We're getting to that. We're going to run it on the quantum computer. So, open questions and future directions. Under what conditions can quantum computers identify these quantities? So we were able to figure out that trace distance and fidelity can be cast as an interactive proof, but what are the generalized conditions under which this should be possible? What are the effects of noise on these algorithms? Because so far everything was run on a simulator, so it's perfect simulation. What happens when you add noise? What happens to these algorithms? Whether these algorithms scale well, that is another problem. So, which is a problem we have faced so far? We've kind of handled it with our optimization approach, but in general, scalability is something to think about. I think that's it. Thank you. Any questions?
Yeah.
So, I have a question regarding the replacement of the all-powerful prover with the
Yes.
Circuit, the parameterized quantum circuit, right? So, I guess I have two questions about it. One of them is, under what limit the parameterized quantum circuit will give you the all-powerful prover? Like, what kind of condition has to be satisfied?
Okay, so the idea is that the parameterized, an all-powerful prover can perform any unitary. That was the assumption. So the hope is that the parameterized quantum circuits, for some set, for some chosen parameters, it can do any unitary. That is the assumption that we made. So there's recently been a couple of papers about expressibility of circuits, and they show that for the ansatz that we use, the hardware efficient ansatz, which is rotation X and then control knots and stuff like that, with a sufficient number of layers, you can cover the entire Hilbert space. It's a heuristic, it's not exact, but the idea is that you should be able to do any unitary for a chosen set of parameters.
Okay, I think you also kind of answered my second question. Okay. Perfect, thanks.
Yeah, I asked a question about how do you take care
Sorry?
How do you take care of that?
The fact that it's unitary? Yeah, so the ansatz ensures that it's a unitary, right? So all we have in our ansatz is
on an ideal quantum computer, it's a unitary.
These are all just qubit rotations and control knots. So overall, it is going to be a unitary.
Maybe you could say a little bit more. I mean, like, I think a lot of people there probably haven't done this kind of work. So, like, can you say a bit more about the parameter shift rule and like
Sure. Yeah.
the thing like calculating the gradient? That's actually done on the quantum.
Yeah. So for most of these ansatz, they're going to have rotation gates and just control knots. So when you want to calculate the gradient of this entire cost function with respect to a particular parameter, the way to do it is there are multiple methods that Qiskit allows. One of them is called the finite difference method, which is the usual way of doing it, which is f of, for example, if this is theta 1, you have theta 1 plus epsilon minus f of theta 1 minus epsilon by 2 epsilon. And then this kid would pick an epsilon. If you can specify a value, you pick that, but the default value is f of minus 5. So it's kind of a way to calculate the gradient of this function. It can intuitively make sense. But since these are all rotation gates and they're all expressed in terms of cosines and sines, there's a simpler, more accurate version of this using the parameter shift rule, which is f of theta 1 plus pi over 2 minus f of theta 1 minus pi over 2 divided by 2. And this is approximate and this is exact. And this is only because it's cosines and sines. You can see that if you just that is cos theta, and you can say theta plus pi over 2, theta minus pi over 2 gives you sine. So the parameter shift rule is what this kit uses. I mean, you can use this also, you can specify an epsilon, but then we always use the parameter shift rule to calculate the gradients. And the gradients themselves are now done on the quantum computer because you calculate the function values by running the quantum computer on this circuit with these parameters, and you can calculate the gradient. So now that if you have some time,
if you try to calculate in the classical computer, that would be hard.
Yeah,
because the
circuit size is big, and that's essentially since we have time, I can show SPSA on that. So one of the things that speed up our calculations is this algorithm called SPSA. So this is a general path update rule where you have your new parameters, old parameters, and a shift based on your current parameters and a step size. And this is the usual gradient descent. You can see it right there. So the shift that you take is theta k plus c delta k. Sorry, this is the original one. Sorry. For each I, you have to do the shift and then divide by that. So if you have 40 parameters, you do theta 0 and then theta 0, then theta 1, theta 2, theta 3. That gives you an entire vector of gradient, entire vector of derivatives, and then from that you get the step size. So as the number of parameters increases, in our case we have 80 parameters, as the number of parameters increases, calculating these gradients are really slow and it just never converges. It just takes too long. So we are using this method called SPSA, which is we simultaneously shift all of them by this vector delta k, which is randomly picked from a Bernoulli distribution. And so the way to think about it is, if you have
might need a better mark.
Yeah.
Okay.
So if this is your cost landscape, and you start somewhere here, your gradient descent would go perpendicular to the field lines and reach your optimal point. So while it takes lesser number of iterations, each step takes a lot of time. But an SPSA would do something like this and reach the same point. But each step is much faster. And since the numerator is independent of I, it can be done in less. So if you have 40 parameters, each of the 40 parameters have the same numerator. So you don't have to call the function every time. Especially in a quantum scenario, calling the function would imply creating the circuit, embedding the parameters, running it, and calculating the outcome probabilities. In this case, the numerator remains the same for all of them, so it's much faster. And it's been shown that this is an unbiased estimator for the actual gradient. So if you run it for long enough, it reaches the same value. But it is faster, much faster. No, in this one?
Yeah.
So delta ki is actually a parameter that has to be chosen by us. It's a set of parameters actually. The thing is, if you don't choose them yourself, it's chosen from the previous iterations standard deviation. So it's chosen in a way to satisfy a few conditions to make sure the entire thing is unbiased.
Any other questions? Thanks, Soorya.